Good afternoon, everybody. I am really happy to see so many familiar faces here from so many different regions. That's really fantastic. So thanks a lot for coming. And I would like to start also acknowledging Tomáš, who is not here, and Jairo, with whom we started to heavily think about this concept and ideas. And eventually it grew into larger collaboration, and many of the people from the collaboration are today here, and I will talk also about papers which we did together. And also I will talk about some newer results which we did together with my group in Dresden and in Mainz. And I would like to highlight that we have also many talks and posters from the collaborators, so we can look forward also for those. And finally, I would like to acknowledge the whole community which was built around unconventional magnets, spin groups, and many other things. And here, Jairo said we had 10 years of SPICE. So 2 years ago, or 2.5 years ago, so 75% of the time, there was organized the first workshop, SPICE workshop on altermagnetism. And there were 70 enthusiasts, many of which are here today again. And since then, we will see during the talk that actually it grew into quite a huge global collaboration. So let me start with the motivation for why we are here today. And the motivation is coming back more than a decade ago, when we were with Tomáš and Jairo heavily obsessed about the idea whether we can somehow combine the benefits of ferromagnets and antiferromagnets. And these benefits are usually quite complementary. So for instance, in ferromagnets, due to the magnetization, you have strong spin polarization, which can be harnessed in some devices, like this MRAM on chip in the latest, actually, magnetism, which made it into some technology. But at the same time, this magnetization is an enemy because it constrains the speed and also the scalability of the devices. And majority of the ferromagnets we know that are metals. So that's why people started to look into antiferromagnets, where these three problems are mitigated, because antiferromagnets do not have stray fields, and due to the exchange enhancement, we can switch them in principle 1,000 times faster. But at the same time, we know that by the name antiferromagnets, many of the effects which we have in ferromagnets are getting cancelled by definition. So for instance, all these spin currents which are used in these technologies, they are absent in antiferromagnets. So
sorry, can
yes?
we ask questions during the talk?
Yeah, I think you can ask.
So is there a fundamental reason that the speed of the ferromagnets is always smaller than the antiferromagnets?
Yes.
It has to do with the
If you
Q squared? Is that?
If you open Kittel, you will have in antiferromagnet the switching J times spin orbit and square root out of it. So the J makes it much faster.
I see. It's basically the gap, right? It is the gap at gamma, which is given by the anisotropy in the ferromagnet.
Well, that's in ferromagnet. An antiferromagnet,
J times anisotropy.
it's enhanced by the exchange. That's the whole point.
Yeah, essentially the idea is that in the ferromagnets, only one is dancing, and the only way to rotate is with a weak relativistic energy.
Okay.
The alignment is done by exchange, but it doesn't come into the dynamics. That's why. But in the ferromagnets, it's 2 to tango, so they actually go faster because the exchange is a geometrical ratio averaging of the exchange and anisotropy. And that's a factor. And this is also natural why it is a factor of 1,000 typically. That's pretty natural.
So now, if we want to do that, it turned out that it might be useful to go from the simple nail-like picture of magnets where we put dipoles on the atomic sides and study their distributions. It turned out that it could be useful to start to think about the full spin density around the atomic sides. And when you look into the two conventional types of ferromagnets and antiferromagnets, you see that the spin densities are isotropic around the atomic sides, so they do not break the underlying lattice symmetries, and that means that the approximation of the dipoles is quite good. However, to answer our question we were obsessing about, we tried many different things, and eventually what turned out to be quite useful was to try to modulate the spin densities around the atoms. So in this example, you see that the spin up and down are now breaking the local symmetries of the lattice, because you see that this has now orthorhombic symmetry unlike the original square lattice. And you also see that these anisotropies are spatially oriented in different directions. So they alternate in some sense. And we will see today that when we start to play with such a compensated magnet where we somehow design the internal distribution of the spin density, we can achieve the praised combination of benefits of ferromagnets and antiferromagnets. And on top of it, we can also introduce some entirely new functionalities, as we will see. So why is this different from conventional ferromagnets and antiferromagnets when we look at it from the very schematic picture? Well, we can now take these two spin densities and we can expand them into partial waves. And you see that we will have here antiferroically ordered dipoles as wave channel. But on top of it, we will have ferroically ordered, in this example, D-wave spin densities, which corresponds to octupoles. And so you see that now this is definitely not a typical antiferromagnetic thing because it's ferroically ordered. So you see that the spin densities are oriented the same on the two sublattices in the unit cell. And you also see that now you have a situation where the spin density is compensated not only within the unit cell, but also within this partial wave channel around the site. So you see that, for instance, for the D wave, you have two nodes. Okay, so now we will see that when we classify this very systematically by spin symmetries, which I will later explain, it's complete for collinear magnets. So we have three types of spin groups, and to them corresponds these three types of magnetic phases. So the question is, when we organize now these guys into this matrix of systems which do not break lattice symmetries, which break lattice symmetries in rows, and in columns, whether they break time reversal symmetry on momentum space or preserve time reversal symmetry momentum in space, apparently there is missing one guy. Yeah? There is missing something which is not available in collinear exchange magnets. So now, if we go to non-collinear magnets, it turns out that we can extend the group theory to capture this situation as well, and we can systematically identify now a situation where we will combine sort of properties of antiferromagnets and altermagnets, in a sense that you see that in a direct space we have the typical antiferromagnetic symmetry of lattice translation combined with time reversal. However, because we will break some other symmetries including inversion, when we go into the momentum space, in momentum space we will have now time reversal symmetric electronic structure. So you see that the difference between altermagnets and now what apparently suggests to be called anti-altermagnets is as important as the difference between ferromagnets and antiferromagnets. So here we have time reversal blow-current systems, here we have time reversal preserving systems in the momentum space.
There is also the issue that in an antiferromagnet you break translation invariance.
Yes?
Because the ordering is at a finite
Yes.
wave vector is not an is not an intra-unit cell ordering. These states do not necessarily don't need to break translation invariance, don't they?
No, but if you consider those states, you will see that you will start to mix different type of spherical harmonics, and you can actually end up with combinations. I will discuss that later.
And they break translation symmetry?
Yeah. So you can have a situation where you break translation, where you still will have odd parity wave, right, but then you will simultaneously break also time reversal, for instance. Okay. So it's not going to be sort of, here I'm talking about 4 basis vectors, let's say, from which you can then build everything else. Okay. And also there are some subtleties, which I will discuss later a little bit as well. So for instance, here are not only this example of time reversal with translation antiferromagnets, but also spatial inversion with time reversal, for instance, would belong there. And then for non-coplanar systems or non-collinear systems, they will belong even more complicated systems, which I will discuss later. But all of this can be very systematically classified for all possibilities. Here, again, I'm just showing few examples to we have some initial idea.
Just for us to get oriented, can
Yes.
you specify what you mean by antiferromagnets being time reversal even?
So again, as I said, in momentum space. So in direct space, of course, all magnets are breaking time reversal symmetry.
Well, they are essentially, time reversal is equivalent to a lattice translation. In that sense, that the combination
Yes.
lattice translation and spin flip is a symmetry.
Exactly.
Okay.
Yes, exactly. Are you happy, Erk, with the answer?
No, this is well defined. Yeah. For me, time reversal symmetry is holy, and I would not define it differently, but it's a free country.
So far.
So far.
Well. Erk, anytime I talk about time reversal, is the holy time reversal.
Yeah.
If I would talk about some other, I would say effective or something
Okay.
else. So I'm very careful. I also am very. Okay, very good. So now we have these 4 building blocks, and I will now talk more in detail how we can classify them systematically, and what other guys we can do, and what interesting physics can come out of it. So this is basically the outline of the talk. In the first part, I will talk how by analyzing these ferromagnetic effects in compensated magnets, we eventually stumbled upon this weird class of magnets, and we realized that we need to somehow start to think about different symmetry framework, how to describe them. And that symmetry framework is spin groups, and it turns out to be very useful for many things, and that's what I will discuss in the second part. And then finally, in the third part, I will discuss about some emerging research directions, which will be also a topic of the conference. So we will see how much we will catch there. Okay, so coming back to the original motivation, when we want to study these ferromagnetic effects, we can choose one particular spontaneous Hall effect, what we did. And spontaneous Hall effect, we know for more than a century that is associated with ferromagnetic order. And if you look into Russian literature from 60s, you will realize that people were trying to do also spontaneous Hall effect in compensated systems. But they realized very quickly that, of course, because you have, for instance, this unholy time reversal with translation symmetry, you will end up with prohibiting the spontaneous Hall conductivity pseudovector. So what they try to do, they try to somehow count the moments, but that would be very often associated with some weak ferromagnetic moment, parasitic weak ferromagnetic moment, which would be very often the attributed origin of the spontaneous Hall effect. And then finally, around 15 years ago, Alan MacDonald and later many others started to consider non-collinear compensated magnets, where they could build systems such as manganese-free tin, and they could induce very strong spontaneous Hall effect. But because we were coming with Tomáš and Jairo from the perspective of spintronics, we were obsessed of trying to build this in perfectly collinear system, because we wanted to have, in principle, very strong collinear spin polarization. So we tried many different things, and then it turned out that the very useful path to go forwards is to start to think about these spin densities. So here is an example of such a spin density which keeps the moments perfectly collinear and perfectly compensated. But when you calculate from first principles for such a spin density anomalous Hall conductivity, you will get huge values as large as for elemental iron. So now, practically, one way how to do it, which we identify, was to take boring antiferromagnetic lattice and decorate such a lattice in very specific way by non-magnetic atoms, that you have encouraging these spatial anisotropies to alternate on the two opposite spin sublattices. And when you do that, you are breaking all the unholy time reversal symmetries, which otherwise would prevent the spontaneous Hall effect. So that was the prediction, and then thanks to many of our experimental collaborators, we were able to grow actually these materials from the predictions, and we were able to measure simultaneously in squid magnetometry vanishing magnetization and quite large remanent spontaneous Hall resistivity. So now this was confirmed also in many more experiments and also in States and in Japan. So we have now a set of maybe 10 materials where this is confirmed that you can have a collinear magnet with zero net magnetization and very strong spontaneous Hall conductivity. And you can go also now into many other effects, because this is spontaneous Hall conductivity. So because you are breaking now these time reversal symmetries, you can go also, for instance, to the Nernst effect. Okay, so at the same time, we wanted to understand better what is going on microscopically and why we have such a strong spontaneous Hall conductivity. So when we calculate for such a system the momentum resolved intrinsic spontaneous Hall conductivity, which is which can be written as Berry curvature momentum resolved, you will see that actually the largest contributions are located along very specific regions in the Brillouin zone, where you have, without spin-orbit coupling, nodes of the spin-split Fermi surfaces. And also what you see that the Fermi surfaces are split in very different way than what we know in ferromagnets, because you see that the splitting is strongly anisotropic. And for instance, for this direction, you see that for opposite wave vectors, we have the same spin. So it behaves effectively like a ferromagnet, very strong exchange split ferromagnet. However, you will always find another wave vector in the momentum space where you will get a perfect compensation. So now all of these regions turn out to be sources of a very large spontaneous Hall conductivity. And then we can look also into the energy band structure, and we see that we have indeed very large momentum dependent spin splitting. And in the first material which we identified by this philosophy, it was more than 1 electron volt in theory. So then also we were calculating other properties, and we have already here realized this sort of D-wave origin of these anisotropic spin densities. I will not talk about it in detail because I believe that Raphael will talk about this different contribution with spin orbit and without spin orbit.
Actually, he will.
Ah, okay, very good.
We're dividing and conquering.
I like it, I like it. So then Jark will talk about it.
I will neglect spin orbit.
Nice. I love both. So here the bottom line is that we have very strong non-relativistic exchange spin splitting, which is momentum dependent. Then we add spin orbit coupling, and interesting physics such as spontaneous Hall effect happens. Okay, so we had few materials, but we wanted to somehow identify whether, you know, it's just them, it's some, you know, bizarre obscure situation, or if we can systematically identify more. And that brought us to think very systematically about symmetries of magnets. And we know that usually what we do, what we are taught since Landau and Shubnikov, we take crystallographic groups, we add spin orbit coupling, then we have double crystallographic groups, and then we add exchange forces, we add magnetism, so we have crystallographic magnetic groups. The problem with this is that here you are mixing the effects of spin orbit coupling and exchange, so it's very difficult to say something only about the magnetism per se, about the exchange forces. So you can instead actually study a lot of mathematical literature, and you will find that there is another way how to do it, and you can first instead add the exchange forces, and only afterwards you add the spin orbit coupling. And this object, these mathematical objects, are crystallographic spin groups. And then after trying many different things, once we hit this thing, it turned out that it can be useful for very, very many things, as I will show later today. So that brought us into the systematic classification, where we were now able to explain that we have actually not few materials, but the whole symmetry class, which is characteristic by having these spherically ordered multipoles in addition to the dipoles, and of having this unconventional characteristic in a sense that you are breaking half of the lattice symmetries by the spontaneous exchange order, and then you need to take the other half and augment those with spin rotations. And then you can go from the direct space to momentum space, and you can calculate the band structure, and you will see then directly in the splittings the order parameters. So here you see splitting for manganese telluride. So now this is experiment which was done by Juraj Krempaski and colleagues in Switzerland, and I think that this is a beautiful result which goes beyond altermagnetism, because you see what we can do with today's technology, that they can grow such a precise layers of manganese telluride and bulk of manganese telluride, and then they can do ARPES resolution that you can resolve these splittings and these magnetic states. So I think this is really beautiful result in general for physics of magnetism and spectroscopy. Okay, so to summarize, you apparently see that these order parameters behave differently than what we know from ferromagnets, where the splitting would be constant, or from relativistic systems such as Rashba systems, where the splitting would be linear in momentum, and also it would lead to non-collinear spin expectation value. So here the situation is different. You have quadratic time reversal symmetry breaking situation in momentum, and you have also spin which is collinear. So this turned out to be very fruitful stream of research, I have shown you one example of anomalous effects, but they followed many, many hundreds of various effects which can be interesting. And then also the framework of spin symmetries turned out to be a very interesting research field. So for instance, Bilbao crystallographic server people are now implementing these spin symmetries motivated by these results to have a classification of thousands of materials in these databases. And finally, the altermagnetism and its application, as we will see also in the next talk by Tomáš, they grew into very quickly quite large field itself. So I would like to here summarize that we have now several materials which were experimentally confirmed, and typically the experimental confirmation of altermagnetism is coming either through indirect way to having some effects such as spontaneous Hall effect without magnetization, or you can directly measure the order parameter in momentum space. So there are various RPS papers I will mention later more. And then you can do also some other experiments in direct space where you can map the order in the direct space. So for instance, here you see the order parameter of manganese telluride, which is detected by X-ray magnetic silk-rod dichroism, which again is effect which breaks time reversal symmetry. So in an antiferromagnet with time reversal and translation, such an effect is difficult to use for such a beautiful maps which are possible in manganese telluride. And I think that also important message is from this works that we have now way how to very systematically achieve large enough domains of manganese telluride. Because still 2 years ago it was open problem whether we can somehow touch and make functional these unconventional order parameters. Because very often in materials these order parameters could come in pairs of domains with positive and negative sign of, let's say, spin conductivity or Hall conductivity, and that would lead to cancellation. So what we have shown in this paper with Nottingham, that we can actually nanopattern manganese telluride into hexagons of micrometer size, and by applying very small magnetic field, we can create very large magnetic domains. So for practical progress in the field, I think this is very exciting, because now we have demonstrated that we have also a way how to really prepare a large enough piece of such an unconventional magnetic system. Okay, so this was first part. So let me now go to the second part, and let me discuss the classification. So to discussing the classification, let me recall what is well established since Anderson and many decades, that what are the unconventional correlated phases. So when we have conventional phases with some order parameters such as superconductors, the pairing wave function gap is isotropic, so it is S-wave channel. And as unconventional, we will define higher partial wave channels which break lattice symmetries. And this is really going to the early days of quantum mechanics. It's really enjoyable to read these original papers from early days of quantum mechanics, where people are asking question whether there can even exist some parity breaking phases, and they are even suspicious that maybe some of them can be explanation of superconductivity, which, if you recall, at that point there was no BCS theory. So this was a hot contender. Turned out that's not the case, but still there emerge some other types of unconventional correlated phases, such as superfluid helium-3 or cuprate superconductors, which have P-wave or D-wave order parameters of the pairing wave functions. And it was also established very clearly what is the theory of symmetry, and the breakthrough there was the thinking of Leggett. What he realized was that even though you have always in the superfluidity some effective atomic spin-orbit coupling, what you want to do, you want to partially decouple the channels. So what he did, he considered factorization of the symmetries into orbital channel and spin channel, and when he did that, he could very systematically describe all different types of unconventional superfluid phases. So that was very exciting. Okay, so how is this now relevant for us? Well, for us in magnetism, the relevant question is whether we can somehow realize the analogs of these correlated phases, but now in spin triplet channel. And for the isotropic case, we know that this is a ferromagnet, because ferromagnet has constant splitting in momentum space. So the question which emerged many decades ago was whether we can realize also the counterpart P-wave and D-wave magnetic phases. And the question is also, what is the right theory of symmetry in analogy to the superfluid helium-3 to look at these phases? And because this field was motivated by correlated phases, people look very naturally to correlated instabilities. And here is an example, for instance, of a beautiful paper from Eugene Chudnovsky. There were also beautiful papers from Eduardo, from Jorge Hirsch, and many others. And what the beautiful physics was about was to consider whether we can cook up some instabilities which would produce such a deformation, spontaneous deformations of Fermi surfaces. Unfortunately, so far, we were unable to find good material candidates for this path. So for today's talk, I will abandon this path and I will go around the many-body problem by trying to build now the systems differently. So instead of being in a momentum space and studying instabilities, I will go into the Dirac space and study all possible spin densities on the crystal lattices. And we will see that when we do that, a lot of useful things starts to pop out all around the place.
Can I ask you a question?
Yes.
So I think in the spin nematic spaces, you don't have another order parameter, right? You don't have a primary antiferromagnetic ordering. You don't have it, basically, right? That's kind of the point. So then the nematic order becomes the primary or only order. So isn't that very different from the altermagnets?
Yes.
But this is not spin nematic in the usual sense. The spin nematic has a triad as an order parameter. Okay. The nematic spin nematic, or this is not equivalent. Okay. The nematic spin nematic is the altermagnet, and it's not the same as a spin nematic.
Okay.
And so there's a problem with the terminology. There's some overlap in the terminology, but they mean different things. The spin nematic has an order parameter which is a triad in spin space.
Right.
Okay.
Yeah.
Cool.
It seems to me that altermagnet you could also define as something like S plus D, right? Where you would say the antiferromagnet is the primary order parameter, which is like a ferromagnet, is a isotropic way, and then because of the anisotropies that are direction dependent in K-space, you get a D-mix, an admixing of D order parameter.
The point is that
Because you would miss then other physics as well. But there's some systems that we're going to show you later where you don't have an S order parameter, but you still have a D wave. So it's instantly, your primary is a D wave. The S wave is not doing any kind of results integration whatsoever. And then we actually have cases where there's no dipole within the atomic. Yeah, you'll go over that in a second.
well, Jeroen, you see here that the S-wave channel is compensated. So the S-wave channel is anti-ferroic, while the D-wave channel is ferroic.
Right? There is antiferromagnetic order.
Yeah.
Is there?
It's
a
anti-
fully default order parameter. And on top of that, or let's say triggered by that, there's another component order parameter, or an admixing of D wave.
So I am not sure I understand your question. What is the question?
Well, so it's the discussion, right? So the discussion could be, or if you look at the Landau theory, then one way of looking at it, like Paul McClarty did, and others, that there is a antiferromagnetic order parameter that is developed, and because of that, on top of that, or induced by that, there's a secondary or pseudo-primary actually order parameter, which is the D wave. Well, I think that is a consistent description of what's happened.
Yeah, well, you can develop.
Without the primary order parameter would also not be the secondary order
The
parameter.
problem that I don't agree. The problem with nematic, spin nematic, or the altermagnet doesn't have to break translation symmetry. It doesn't have an ordering wave vector. So you don't need antiferromagnetism.
You will see an example later
Yeah.
of the D wave altermagnet that has no L vector.
Then it's not antiferromagnetism, it's a zero momentum state.
Yeah.
So it's a translation invariant state because the ordering wave vector is zero. Okay. So you may need lattices with more than one unit, with more than one atom in the unit cell, But once the lattice is formed, it's translation invariant. There is no anti-ferromagnetism.
It's not necessary.
No, it's not. I mean, unless you break translation symmetry.
But if
I
you
mean,
do-
it's like in graphene. If you break the symmetry between the A and B sides, the two cell lattice is an intra-unit cell ordering and has vanishing ordering wave vector. Okay. So it doesn't break translation symmetry in that sense. So I think one has to be careful when you have a multi-cell lattice system with more than one atom in the unit cell. You can get this physics without breaking translation bias. You may also break translation bias. That's a separate question.
Yeah. So I think that was a very nice comment. I will progress, but we can also, when we have the discussion time, we can discuss it more. But for time being, all the useful things you don't need to do what you were suggesting, Jerome. For all the things which I will be talking about, you can just go with the spin groups. Okay. So how we build these spin groups? It turns out that there is very subtle point how to define the operation of recoloring the spins. So this could be spin density instead of this horseman in Escher picture. And usually what Landau and Shubnikov did when they wanted to go from the one color to the other, they associate this recoloring element with time reversal. But what it implicitly does, it implicitly couples the spin and lattice. So you have implicitly spin-orbit coupling there. And then it turns out, if you study a lot of beautiful papers from Koiner-Sering from 1940s, he was toying with the idea that we can define something more general, where we, instead of time reversal, associate this recoloring operation with spin inversion or spin rotation. And this might look like a very subtle point, but we will see that this has many implications. And I would like to also remind that both of these approaches, magnetic groups and spin groups, are approximations. Because we know that even for the magnetic groups, we are thinking about some spins, which are, like approximations to Dirac equations, and these are approximations to more complicated many-body problem. So I think it's good to keep in mind that the different approximations can be useful for different things. So now, in terms of the construction, you see that in the conventional magnetic symmetries, we are applying consequently the operation simultaneously on the spin and lattice. So for instance, 90-degree rotation would rotate both the lattice and the spins. So you see that such an operation is impossible to build into symmetry of the crystal in this example. However, if we now allow these pairs of operation and spins and lattice space, we can cook up operations which combine 90-degree rotation of lattice space with 180-degree rotation in the spin space, and this is now a beautiful symmetry operation of the lattice. So when you partially decouple these two spaces, you end up naturally with many more possibilities. So for instance, for magnetic symmetries, we have this famous 1651 magnetic Shubnikov space groups. The counterpart number of spin space groups is more than 100,000. And that's a number which we obtain if we consider propagation vectors up to 8 unit cells. Because if you consider infinite number of propagation vectors, you will have infinite number of possibilities. But to keep some bookkeeping, you need to cut it somewhere. Finally, when you do this process, you also end up describing much higher energy scales. Because once you, in the magnetic symmetries, are coupling the spin and lattice, you have the spin-orbit coupling. So typically, you start to describe effects such as magnetocrystalline anisotropies, which are on very small energy scales. By contrast, in the spin group framework, you are now describing the exchange-driven contributions to the Hamiltonian. So they are corresponding to much higher energy scales, which can be electron-volt scale, as you have seen in the beginning of the talk when I was showing the momentum-dependent band splitting. Yes.
Has anyone, has people tried to do that for incommensurate structures, like using the supergroups? Because, as you said, right, if you keep increasing, you're probably going to get just a mess.
Very good. No, there is no paper which would do it systematically, and you should do it especially because you have a material.
That's what I was thinking, because there are these incommensurate materials that
Yes.
have this very similar.
Yes. Yeah. So you can do it. It wasn't done. And it should be done. Okay, so another difference between magnetic and spin symmetries is when we look now into manifestly different orders. So here we have collinear compensated ferrimagnet. Here we have some non-collinear compensated magnet, which we know, thanks to Alan, that it has anomalous effect. And finally, here we have the rutile altermagnet. And when we look at the point symmetries from the perspective of the conventional magnetic symmetries, we see that all three phases have the same magnetic point group, which combines mirrors with time reversal, which is marked by prime. So you see that the magnetic symmetries, although they are super useful for many things, here they are not that useful because they cannot even distinguish between collinear and non-collinear magnets. Now, when we do the same exercise with the spin groups, we see that we have now manifestly distinct spin groups, and we can already on the level of something what is called spin-only groups, which are acting only on the spin degree of freedom, we can already on this level distinguish between collinear and non-collinear magnets. So for instance, for collinear magnets, we will have always operations which are combining into binary group identity and time reversal combined with spin rotation. And we will have all these rotations around the axis of the spin, spatial rotations. So once we go to non-collinear magnets, we break this continuous part, and we end up only with this coplanar symmetry. So in this way, we can very neatly distinguish whether we have collinear, coplanar, or even non-coplanar magnet, where you would finally break this. And then finally, you can study what is happening with these objects. So you need to now multiply this spin-only group with this so-called non-trivial spin point group. And here you see that you are now having various different combinations where the small index corresponds to spin space operation and the large corresponds to the lattice space operation. So you see that you have manifestly operations which are not allowed in the magnetic symmetries, because you see that you can combine 3-fold spin rotation with 6-fold lattice rotation, for instance. Okay, so let me now, for the sake of brevity, focus on collinear magnets and see what happens there when we do the systematic classification. So we are able to identify these types of groups which correspond to the conventional ferromagnets and antiferromagnets. So for ferromagnets, you see you will have no operation which would be augmented with spin rotation. That makes sense because you have magnetization. While for antiferromagnets, by definition, and as Eduardo was already explaining, we have, for instance, this lattice translation. So effectively, for each lattice operation, there exists also operation which is augmented with the spin rotation. And then when we do all possibilities, it turns out that there is yet another possibility. And this is the third type possibility, where you now break half of the lattice symmetries, and you take the other half and augment those with spin rotations. And it turns out that these are exactly the groups which correspond to the altermagnetic orderings, where we are combining the S-wave dipoles, which are antiferroic, with the, for instance, D-wave ferroic spin channels. We have seen that this was now experimentally confirmed in RPES for electronics degrees of freedom, and now there are also some experiments which confirm our magnonic predictions. So even the magnonics degrees of freedom are inheriting these characteristic symmetries of altermagnets.
Well, in what sense they are chiral? The terminology, but
this is abusing the terminology. I wouldn't call them chiral. Yeah.
okay.
Yeah.
So
It just means that that's handiness. That's all. Yeah. Yeah. There is.
One is this, the other
Yeah.
is this.
well, okay.
Chiral in a very well-defined.
Well, I don't think we need to go into the discussion of what is chirality. Because
Magnons can be chiral, right? Also in antiferromagnets, magnons can be chiral. And you can calculate also the spin of the magnons
Yes.
in these cases. And in these cases, the magnons actually do carry this. Vladimir, who was sitting next to me, has a very nice paper on that.
yeah, that's true. I agree. But when I'm talking about the symmetry and group theory, there are things which are called chiral groups and concave groups.
That's something else.
So we shouldn't. These are two different things, exactly. Okay.
Chirality is the most abused word in theoretical physics.
So exactly that's why.
In other words,
That's why I will move on from. That's why I will move from this magnons. Okay. So important message or important bottom line of this exercise is that this is complete classification for all collinear magnets. And that leaves us again, as I was talking about it in the introduction, with this remaining piece when we try to organize them according to whether they break the lattice symmetries, whether they preserve the lattice symmetries or break the lattice symmetries spontaneously, and whether in momentum space we have time reversal broken states or time reversal preserving states. And we can now use the spin groups to apply to non-collinear magnets, and there we will identify actually a large class of magnets which will have yet another group structure, where now you are breaking again some lattice symmetries, but now you are breaking also inversion. So that's a very different situation than before. Now you are breaking inversion, and then you are taking the same symmetry operations and you augment them with spin inversion or with time reversal. So when you do that, you end up having these states in momentum space and in direct space. So apparently here I am again recalling ferromagnets, antiferromagnets, and altermagnets. And you see that now in this last class of anti-altermagnets, which I have introduced in the introduction part, you see that we have now a very bizarre situation, because in momentum space, the spin polarization points in a direction which is perpendicular to the direct space of the coplanar non-collinear order. So you see that this is a very different situation. So let's look into the origin, and the origin is the spin-only group I was talking about before. So because these coplanar systems have this binary group which includes as element time reversal with twofold spin rotation around axis perpendicular to the plane of the direct space spins, this operation you can try yourself will force your spins to point into the perpendicular direction. So let's look into this class in a little bit more detail. And here I am showing example of cerium nickel arsen oxide, which was also studied by Daniel. I think he will talk about this in more detail, so for the sake of time maybe I can skip. Not you? Damn. Brian?
No, but I'll talk about different materials.
Okay.
But I'll talk about this topic.
Then I will talk about cerium nickel arsen oxide. Okay, so in these beautiful calculations from Anna, you see that when you go through the phase transition, you end up with this time reversal symmetric spin splitting. And you see there's also anisotropic, and there is some extra symmetry, some mirror symmetry, which protects this single spin degenerate node or spin unpolarized nodal sulfase. Finally, when you look into the electronic structure, you see that again you have large momentum dependent spin splitting, but now the difference is that while in altermagnets we had quadratic time reversal symmetry breaking case, here we have linear time reversal symmetry preserving case. And you see that the in-plane spin components are counterintuitively 0, while the out-of-plane spin component is non-zero. So that's yet another difference, and that's also a difference to the Pomeranchuk instabilities, that we have now a state where the spin magnitude or spin polarization magnitude depends on the momentum. Here I would like to remind that, but we discussed it a little bit, that the beautiful paper of Rafael, Ricardo, and others, they have shown that you can have indeed such a time reversal symmetric spin polarization or antisymmetric spin polarization, but the system itself is most likely not fulfilling the pure definition of anti-altermagnets because it's incommensurate. So we are waiting for your theory.
It's coming.
Sorry, yes?
So since you brought it up,
I want to make this point clear. Yeah?
so the difference, and Jorn is here actually, we discussed, Jorn is also in the paper, and so if you have a spiral that is an even period spiral, you satisfy all the conditions that Libor said, and then at gamma point, you get all these Kramer's doublets that are crossing. If the period of the spiral is odd, then besides having all this, there's going to be an additional known Kramer's point at gamma that essentially, if you Libor was to plot there, the spin polarization would be exactly 0 at that point. So that's the only difference. Now, incommensurate is in between both, right? But you have the same symmetries whether you want to define anti-altermagnets as they have to have Kramer's doublets everywhere in gamma, or if you allow it to have just one that is not.
Well, they would be somewhere in the matrix as a mixture. So. So then you can look into some interesting effects in such a system. So for instance, since you have this beautiful anisotropic spin splitting, you can expect quite large transport anisotropy, and that's indeed what in these beautiful calculations from Anna and Atassi we see. So we see that you can have around Fermi level even 60% difference in the resistivity in the two perpendicular directions, which in the non-magnetic states are perfectly having perfect square symmetry. And then finally, we can also look into the spin response. And there will be talk by Atassi, so I will also not talk much about it. I would like to just highlight that when we apply the electric current, we can induce homogeneous spin polarization, aka Edelstein effect. And the Edelstein effect will inherit the symmetry of the order parameter of the p-wave magnet. So I think that's again very exciting. Geron and Mengele have a paper about it, so I don't know if they will be maybe talking about the non-relativistic Edelstein effect, maybe not. And yeah, there will be several papers on several talks on this topic, so I will leave it at that. But I think the beautiful message is that we can have some spintronics effects which can be detected, for instance, by MOOC, which inherit the symmetry of the order parameter. So you don't need to necessarily go to ARPES. You can also do some tabletop experiments to study the order parameters. Okay, so now finally I would like to show now these four basic states and some other materials which quite counterintuitively belong into one or the other class. So for instance, there is a nice work from Yuri, and then there are some works from Japan, from Yuri Mokrosov, where they have shown that you can have magnets which are non-coplanar, which break time reversal with translation, which break spatial inversion with time reversal, but still they have so-called spin translation group, which is sort of permuting the different spins and rotating them, and this symmetry will enforce your bands to be Kramers degenerate. And then finally, you can ask a question whether you can have also situations which were originally envisioned by Eugene Chudnovsky in the 1970s. And this would be a state where you have this isotropic lattice channel combined with this hedgehog vial-like spin texture. So let's look now into this problem. So this is taken from a paper from Marchenko from 1991, where they were trying to identify such a state. And now with the spin groups, we can find the answer. So we can build the lattice, which looks like this, and then when we calculate the simple minimal Hamiltonian for such a guy, we will obtain this beautiful hedgehog, where the order parameter again is clearly distinct from the conventional magnetization or from null vector.
The blue points, are they spin out of the plane? No.
In the plane.
So this is not non-collinear.
Yes, exactly.
But it's coplanar. The blues, they're not.
These spins are non-coplanar in the direct space, and in momentum space, these are coplanar in plane.
So there are some pointing in and out of the plane issue.
They are in the plane. They are coplanar in the plane.
Yeah. Okay.
They are in the plane. Yeah. So they are really, this would be kx sigma x plus ky sigma y. Yeah.
Is this an ultramagnet?
This is not altermagnet. We are coming to there. Because it does not break time reversal symmetry, so it cannot be altermagnet. Yeah. By definition. In momentum space. So in momentum space, it doesn't break time reversal symmetry because you see that for opposite wave vectors, you have opposite spin. So it manifestly preserves time reversal symmetry.
To the left picture, which to me breaks the number.
This of course breaks time reversal symmetry. Yes. But that's not the point. The point is that you are trying to identify.
From the K sigma.
Yes.
The Brexit version and there's a pseudo scalar.
Yes. Yes. Exactly.
That is the Cairo.
I decline to comment on this point.
So it's not break time reversal. You have a translation with time reversal.
It's not the whole.
Well,
Can I make a comment?
Yes,
I think there's a community. When you say that it doesn't break time reversal in momentum space, some people you see have heart palpitations. But I think you just mean that if I combine time reversal and translation, I get an anti-unitary operation that acts as time reversal and therefore guarantees Cramer's genesis.
So I'm always very specific. So I think
So
there is no ambiguity.
No.
There is time reversal in momentum space, and there is time reversal with translation in direct space. That's it. There is no ambiguity there. Okay, but
Normally we would not call them just time reversal. Just time reversal in itself is something different. It's not just something that is.
So Jerome, you wouldn't call. So Jerome, you would.
The question is when you measure it, you know, you have a time, it is time an element, a point group element.
I don't necessarily agree. Maybe it's that Hall breaks spin rotation symmetry, but not necessarily time reversal, because the spinematics that we discussed before, they do not break time reversal. And they are still considered order phase.
So we'll cut that now, 3 o'clock again. We're gonna have a lot of fun this week.
But Jerome,
I have a whole cellar that we can drink to.
but Jerome, wouldn't you agree that this momentum space spin order preserves time reversal symmetry?
So it is a band structure or some structure that is.
So yes, no, it's yes, no.
Which is different from saying, and you cannot see which order. And you're talking about order.
It's
order is a real space.
it's no.
It's symmetry. So it has an invariance if you combine it with translation.
So that was yeah.
I'm just saying that I'm in the field. I like it. It's good. But if you step away from this room and outside this field, and you say that the left guy does not break time reversal.
I didn't say that. But nobody said that, Jerome. You are not listening what we are saying, I am afraid.
So, no, but if the left picture breaks time reversal and the right picture does not break time reversal, we have a problem, because one is the momentum space and the other is real space. So we have to decide.
But I am always, Jerome, you are not listening to me. When I say time reversal symmetry momentum space and I'm pointing here, I am not talking about the left picture. I'm talking about this picture.
Yeah, I know. And on the left picture,
But I think the worry is a given system should break time reversal symmetry or not, regardless how we look at it. I think this is the concern, if I may.
Okay, but then
it would be nice to have a language that would reflect that, or maybe it's not
Well,
nice.
the
but
figure
for-
on the left,
Yeah.
if you
Yeah.
flip the spins,
Yeah.
and you make
Yes.
and the lattice combine with the lattice
Exactly.
translation, it's a symmetry.
yeah, it's a symmetry.
Okay, so in that sense, I mean, it's like an antiferromagnet. Okay.
Yeah, exactly.
Now, you want to call an antiferromagnet something that breaks time reversal? I don't. It's just like that.
I do.
So I think I will start to write here like a blackboard, you know. And by the end of the week, we will see which one got more votes.
I think I am in the minority.
Some people say macroscopic time reversal symmetry, where you just regard translation.
No, Kirill, we are just going with this. So broken, that's we said, and preserving. So we have Eduardo. And we have Jerome.
One can make a distinction. Break time reversal microscopic.
No. You cannot talk around this point. You need to make your choice. Okay. So let's.
Other people's names.
Yes, I will. That's the point. But let me finish. Well, yeah, exactly. So we should decide what we do.
This week, it is relaxed this way. You've noticed that the talk is for 30 minutes, but there was the starting of the break is 15 minutes later, which already were in a break, but with lots of talk. I much rather concentrate with you guys, have lots and lots of this type of interruptions, lots of discussions with each other. We have plenty of time. But that's okay. Anybody wants to take a break? The bathroom is over there.
No, I was.
Because if you, for instance, have an almost Hall effect in an ultramagnet or in an antiferromagnet, it breaks its time reversal off. And
Yeah, but
the Hill
in
vector
an
depends on the direction of the Hill
No,
vector.
in an altermagnet, in some altermagnets you will have it, and some you don't.
Yeah, that's
Okay.
true. You can have
And
it, but if you
in
have
an
it,
antiferromagnet with spin over coupling, you will not have it.
but it couples to the Nail vector linearly. So therefore, it has to be time reversal broken.
Jerome, I'm following all what you say, but I think again, when we say specifically what we mean, Cannot we try to agree instead of trying to disagree?
No, it's not about agreeing, disagreeing, but I like the idea that you talk about one system, either in case space or real space or any space, but we decide that it is time reversal broken or not depending on the picture you're pointing at. That is very confusing for.
And usually, if you have time reversal breaking, you cannot compensate that with another symmetry, with another operation. That's a distinction I want to make.
Mm-hmm.
In an antiferromagnet, you can compensate that with a translation.
Mm-hmm.
Okay, you can say time reversal is equivalent. That's a good translation.
Mm-hmm.
But the good old days we would have called this a time reversal times translation is a symmetry.
It's a symmetry. That's what I'm saying.
No,
That's
it's not what you're saying. You're saying
Yes.
time reversal is a symmetry. And I'm saying time reversal times translation.
Sure, it's a symmetry. No, that is what I'm saying.
Yeah.
Sorry.
But if you only care about macroscopic properties, then spatial translation doesn't matter. So if you're interested in, does it allow an anomalous hole, for example? If there's time reversal combined with translation, it forbids.
Under those conditions, I agree.
But
But I am interested in
macroscopic.
microscopic properties.
No, but
Yeah.
my
No,
argument,
but-
my argument is exactly.
Then it's time reversal symmetry.
No, it's broken, because if you reverse time, you reverse the sign of the whole of it. You reverse the time. You reverse time, you reverse the whole.
Yeah, but
So-
translation doesn't change anomalous hole, right? So with this symmetry, it forbids anomalous hole.
Yeah.
So both microscopic time reversal without translation and the one like this with translation, they both forbid anomalous hole.
Remember, Jerome,
That's
for
correct.
transport properties, any translation is irrelevant. It's the Newman principle. Now, the Newman principle is
No,
that
it's not
the point
really.
group, sorry, it does. The point group symmetry is the one of the determines. You cannot determine of.
So if you have your, but that's very basic. If you have your anomalous hole response, it depends on the direction of the nail vector. If the nail vector is up, the response is like this. The nail vector is down. It's like this. So it is the translation actually that changes the sign of the.
Not that translation is not changing that sign.
If there is a translation that changes the sign, then the anomalous hole is zero.
It's okay. It's
That's
not
the
the full translation. It's the half translation. It's the okay. The time reversal changes the anomalous hole current.
If it's allowed to be there.
Yes.
1%.
And time reversal switches the spins from like the nail vector from like this.
So can I have suggestion? I suggest who is interested into this discussion, we make separate meeting, and I will try in the limited time finish something. But I really appreciate that we are all excited about time reversal, and I'm sorry that I cannot satisfy all of you with the way how I'm trying to.
Libor, is there a material that you're proposing?
Yes.
That one.
Exactly. Yeah. That's the whole point, that we have now a material, and this is the material, and here you see the DFT calculations of the electronic structure, and you can in the material on demand control actually the spin polarization binding. I'm especially for you not saying chirality, but the binding by swapping. If you see here what I did here, I changed the gauge fields coming from some of this. Yeah. Okay. So
Which material is this? Or?
I cannot say.
Oh. Right later and forget in your room.
No, but it's almost on archive. So.
Oh, I see. It's not on archive. Okay.
Yeah. And there are many interesting things about this, because then when you study also the representations, you can find that you can realize some projective representations which are unavailable in magnetic space groups. But since we cannot agree about time reversal symmetry representations, I will not go into this because this requires much more mathematics. And exciting thing from perspective of applications is that this type of magnets can emulate the effects of relativistic spin-orbit coupling, but on much higher energy scale. So you can expect again much stronger effects. And I think regarding in how many areas spin-orbit coupling is useful, this shows that we can have now a way how to do it on higher energy scale, and also have some on-demand control by coupling to the mutual orientations of the spins.
Sorry, can I?
Yes.
This is very interesting to me.
Yes.
That so this is the winding number 1, right? So that would be an odd parity still.
Exactly.
So Eduardo had this whole winding number 2 would be. Do you have a realization?
Yes.
Okay.
Yes.
But you're also not going to tell me.
By the end of the week, maybe.
We're gonna go drink later.
yes. We can go for a drink. And in fact, it was motivated. This project was partly motivated to finish it by Eduardo in some of our email exchanges where he mentioned that, what about the B-type? So can we have some material for it? So here is the material.
Is there material for that?
Yes, exactly. So I wanted to show it especially for you because I felt I owe you this for over a year. Okay. So.
Because I had the understanding that people claimed it was not classifiable. But,
yeah.
Okay.
And now we have material. Even people are trying to measure it. So, very good. So now when we go back to the overview of the different types, so then you would have, you see here you would have this B type with winding 1, which breaks inversion but preserves time reversal. But then you can of course cook up some mixtures. So we have Rafael's and Ricardo's incommensurate nickel iodine 2. But we can have also some other guys which would more correspond to what Eduardo was mentioning. For instance, you can have no time reversal with translation in the system, but still you can have a P wave combined with a G wave, and that what Naira have shown in her paper how this type of combinations can emerge. But very roughly speaking, I think it's good in physics always to have some meaningful classes. So when we have over 100,000 of spin space groups, that's too much. Like having too many classes. But if we want to classify them by just this whether they break or do not break lattice symmetries and whether they in momentum space are preserving time reversal symmetry, then you can find these 4 basic building blocks, and then all the others are some sort of combinations of those. Okay, so this is now what also in our grant in Germany we decided that we will study and discuss as unconventional magnets by the original many decades long analogy with superfluids and superconductors. Okay, so this was the second part. I'm happy that I managed second part. I'm really excited that we are discussing. So Jairo, you are the boss. So what shall we do now?
After you guys, is it okay to continue another 10 minutes? Then we'll have a break of 45 minutes. All right, let's do it.
Okay, then I will. Yes.
In the first part of your talk, you said you are obsessed. You had been originally obsessed with collinear spin textures. Now, in the second part, you said, forget about this non-collinear, this collinear spin textures, the non-collinear ones. To say isomorphic, the relativistic ones isomorphic to the collinear ones, where you get much larger effects. So what should we expect to the third one, for your third talk?
There will be obsession. There is coming a twist. There is coming a twist that the non-collinear ones can be actually collinear. Yeah, so...
I'm coming from non-collinear magnetism. For me, it was... We had basically all the effects in momentum space, but of course not collinear, but in principle isomorphic to collinear plus spin orbit.
Mm-hmm. Yeah, so I will be touching exactly sort of this topic.
But we went a little bit by steps,
Yeah.
It was not exactly from collinear to non-collinear. In the steps of the P wave, we went to non-collinear in real space, but collinear in momentum space.
Yeah, but the last one was not collinear.
Yeah, but so I think I feel a little bit like a politician today. I didn't claim that non-collinear things are not exciting. I just said that our original motivation was the obsession with collinear systems for particular spintronics applications. Spin orbit coupling, super exciting physics, Kirmion, super exciting physics, non-collinear systems. So I am not constraining myself for the rest of my life just to collinear systems.
Because the system is full of non-coplanar.
Yeah, exactly. Yeah. Non-coplanar in direct space. Yeah. Nice. I like the comments like that. Thanks, Stefan. Okay, so let's try to look into some applications. So first thing is magnetoelectric effects. So usually when we have magnetoelectric effects, we are coupling electric field and magnetic dipole. So the question is whether we can couple electric field and now these octupoles or D-wave altermagnets. And the answer is yes. I will show you directly the answer because we don't have time. So you can actually build subclass of altermagnets which are ferroelectric, and then you can build subclass of ferroelectric altermagnets where you have effect which on non-relativistic level couples the D wave and the ferroelectric polarization. So what happens is that you take such a crystal structure and you rotate this fluorine octaedra around these magnetic atoms, and the sense of the rotation is known to change the spontaneous electric polarization, but we have now shown that simultaneously this non-relativistic rotation of the octaedra can change also the orientation of the D wave spin polarization. So you see that I went from one sign to the other, as also confirmed in the DFT calculations in momentum space. So we can now couple directly by electric field, directly access the unconventional D wave order parameter. So I think that's very exciting. And here we did a classification for all altermagnets and anti-altermagnets. And here you see the numbers. So we adopt the terminology which was done also by Daniel Komsky and Jerome, where when we have type 1 ferroelectrics or multiferroics, we are talking about the different origin of magnetism and the ferroelectricity. So typically the ferroelectricity can come from some ionic displacement. And when we are talking about type 2 multiferroics, we are talking about spin-driven multiferroics. And there are two different classes. So one of them is again entirely non-relativistic. The other class needs for the polarization to emerge spin-orbit coupling. And so what you see that the altermagnets tend to be of type 1, while the anti-altermagnets are all over the place for various different reasons. And Jan, my student, he did a really amazing job in calculating a few of those. At the beer, I have a few candidates for you, Rafa.
That's okay. I'll vote for him.
Okay, so this was effect which is non-relativistic multiferroic effect. Now let's go a little bit to what Stefan was asking about. Where is the last twist? So the last twist is now going into 2 dimensions and trying to see what happens when you add spin-orbit coupling. So we can start with antiferromagnet, which has time reversal with spatial inversion combined symmetry now. So it's a system which does not have a lattice translation with time reversal. It's different there. And when we stack it like this, we end up with a known ferrimagnetic situation. But when we do such a different ordering and we put it on some substrate which induces electric field, we are able, this PT symmetric system, turn, functionalize into an altermagnet. So that's work which we did together with Igor Mazin. And then finally, there is another class where we can stack them like those. And these guys will end up having, again, type 3 spin groups, but they will have no splitting in the kz equals 0 plane. You can recall that when I was talking about manganese telluride, it has this G wave order parameter, so the kz equals 0 plane is spin degenerate without spin-orbit coupling. So you can think about this 2-dimensional situation, that this is a sort of 2-dimensional case of manganese telluride. So now we try to classify all possibilities, and we have identified that we have this 158 spin layer groups which have the symmetry of an altermagnetic case. And here you see the classification into the DG and I wave. And finally, here are those which, without spin-orbit coupling, you find them that the nodal plane is directly in the plane of your monopolar system. So these systems are sort of hidden, or we call them weak altermagnets. And let me show you now some practical examples and what exciting things can happen. So first example is which we studied with Igor. So we have some sort of Lie lattice, as Raphael likes it, Lie lattice derived system, where, however, we generate this topological crossing close to the Fermi level. And when we calculate the spin Hall conductivity, it's perfectly quantized. And the origin of the quantization is that we have here now this effective U1 symmetry. So I think that's something again similar, maybe what Daniel will talk about, or maybe not, about some approximate symmetries. Brian will talk about it. Very good. So I'm happy finally somebody will talk about it. So that's yet another role how we can cook up symmetries which are beyond the conventional framework and which can be useful for some observable effects. So here is example of symmetry, which is strictly speaking not a magnetic symmetry, not a spin symmetry, but it's some effective symmetry which emerges in this Hamiltonian and which protects the quantization of the spin-hole conductivity. We can extend these theories into some other effects, for instance, spin circular photogalvanic effect. So that's what we did with Shuichi Murakami. But for the sake of time, I will skip this part. And I will look into this question. I will look into the question what now happens with adding the spin-orbit coupling on top of the altermagnetic perfect collinear spin polarization. And very often, so you can think about this system such as ruthenium dioxide, which is two-dimensional. It's osmium, oxygen 2. And what happens is when you calculate the spin polarization in momentum space in the presence of both altermagnetism and spin-orbit coupling, you see that you have here a strong non-collinearity. So the spins are winding. So you can think about them as a combination of some non-collinear spin texture from Rashba plus some collinear spin polarization out of plane of altermagnet. So the question is, can we identify among these two-dimensional candidates systems where even when we add strong spin-orbit coupling, we will still have perfect collinear spin polarization? And Varley and Jan, they did a very systematic classification, and that they found that indeed there exists quite large class of systems where no matter how strong the spin-orbit coupling is, you will end up with perfectly collinear spin polarization of a D-wave symmetry in momentum space. So you will have this persistent collinear altermagnetic spin polarization.
But sorry, this is only 2D, right? The moment you have 3D, this is impossible, right?
Bam! When you go into 3D, what happens is that you will have it on some sections.
Right.
So example of this is our favorite manganese telluride, because there you have this G-wave plus spin-orbit coupling, and you end up at the kz equals 0, which without spin-orbit coupling is spin degenerate. You end up with the spin-orbit coupling with collinear, perfectly collinear spin polarization, but it applies only to kz equals 0. But still you can think about a system where the semiconductor has close to the Fermi level only states at kz equals 0. So then I think these are for spintronics still super exciting systems for various different reasons. And you see that similar situation is happening also in cuprates. So this is both in monolayer cuprates and also in three-dimensional cuprates. You can have these spin textures, but here the spin-orbit coupling is quite substantially weaker than in the manganese telluride, so around the Fermi level. So what happens is that actually the accompanying splitting, relativistic splitting of the nodal surface leads to quite weak spin splitting, while in the manganese telluride the splitting is quite large. So I'm again recalling that this is consistent with the already published experiments from Uri, where you see that here you have this spin-orbit coupling assisted D-wave spin splitting in the momentum space RPES. Okay, so this brings me almost to the end. So I wanted to highlight that there will be also talks about what happens when you add not spin-orbit coupling but correlations instead. And a lot of exciting things can happen. I think maybe Johannes will talk about, and maybe also Eduardo will talk about superconductivity. So I will just highlight that in the beautiful work of Valentin and Johannes, they have shown that you can, by electronic correlation, induce this unusual situation where you have sort of staggered these two potentials, and then you end up with having staggered orbital ordering and staggered magnetic ordering, and this will end up exactly with altermagnetic symmetry. So it's sort of correlation stabilized orbital altermagnetic state. And finally, here are calculations from Laura Klassen group, and what is interesting there is that you can take a two-dimensional altermagnet and you can study on top of it some correlated instabilities. So even though we know that the instabilities seem to be not the favorable path to the stabilization of altermagnetism itself, the correlation can still, on top of the altermagnetism stabilized by some of these other methods, they can generate some interesting and exciting correlated states. So here we have shown that you can have some spin density waves, and you can have also some part of the phase diagram where you can have singlet D-wave superconductivity. But again, I think Eduardo will have much more exciting lecture about that. So the interesting thing here is that some of these spin density waves actually have been seen in experiments from China on quasi two-dimensional altermagnets. So I think that's actually quite a neat situation where the correlations are really stabilizing some interesting state. Okay, I will skip the spintronic part because we have Tomáš here, and Tomáš will talk about spintronics, right? Also.
Yeah.
Can I skip it?
Skip it.
Yeah, very good. I put so much effort into this one. Okay.
Okay.
This brings me finally just to maybe show this, that we have many more fields about which we will be talking about, and finally highlighting the ever-rising number of candidates. So at the moment we have more than 70 anti-altermagnets, and Daniel have quite a few more. How many did you have in your paper?
Only 20 more.
So that's good. We are almost.
How many of these are candidates, and how many of them are actual cycling?
And actually experimentally proven are these materials so far. But I think that if the neutron scattering data are reliable, I think there will be actually many more materials confirmed.
Manganese difluoride, I know, I mean, that's also being observed before, but it is an altermagnet.
Manganese difluoride, for instance, magnons are not split.
But that's just a resolution.
But there's a
problem.
new paper. There's a new paper.
Yeah, there's a new paper with a sufficient resolution.
Okay, so I was very conservative this time. I just put here those which were looking very convincing, but I agree with you that there are, of course, more systems which potentially.
Depends on what you would call confirmed, right? You're saying confirmed that the spin splitting is observed.
Yes.
Which is a very
very direct.
But manganese difluoride in the 70s, they saw piezomagnetism, which can only be altermagnetic. So
that's another field.
Yeah, but that's an indirect. There's a lot of Thomases, but they need to see the arrows. Without that, they wouldn't believe it.
A lot of who?
Thomases.
This one or
No,
the
like
same?
Thomases from the Bible.
So
We are in Gothenburg.
Could they do the spinography?
Exactly. I agree with you, to be honest.
That's what it is. Yeah?
But, okay, great. So thanks a lot for surviving this talk. And let me just end up on a positive note that from 70 people, I've been a few weeks ago in China, and the conference, which was focused on theory on spin groups, have been seen on WeChat, which is sort of Chinese Facebook, more than 66,000 times. So so I think we have a great opportunity to work now on a theory which few people seem to care about. So I think that's exciting, and Rafael, Jerome, and others are organizing this beautiful workshop soon. Okay, thanks a lot. Looking forward for the week.